Okay, let's start.
Yes.
Good afternoon, everybody.
Yes. Good evening.
Okay, good evening, Mr. Yang. And it gives me a great pleasure to welcome our colleague and partner from Behind University School of Electronic Engineers. And it's really our most profound, and we feel very much highly gratitude to continue this partnership in these actually lectures, which is very important. And Mr. Yang from Behind University, he will today deliver a presentation under title of GNSS Reflections and its remote sensing application. And just to give a brief abstract about the background of Mr. Yang, he is actually a full professor from Behind University. In the meantime, he's at School of Electronic and Information Engineering. He has graduated from Behind University and got his PhD degree in 2000. After that, he joined the research team of GPS Center in Nanyang Technological University of Singapore and worked around 2 years. And from 2003, he worked as an associate professor and a professor since 2010. His research interests in GNSS and its remote sensing. He published about 50 papers in IEEE journals in English and 2 books on GNSS in Chinese with his PhD students and master students and some foreign students. He currently is the Chinese coordinator of China-Europe GNSS Joint Research Group and the senior member of Chinese Electronic Institute. Let's, on your behalf, welcome Mr. Yang and our also friend, Professor Qian. And today we are lucky that the coordination of these lectures, as normal, will be with many Arab and local organizations who deals with astronomy and space science. So please, you are welcome, and it's your floor.
Okay. Thank you, Professor Avani.
Thank you.
So can I share the screen?
Yes.
Good afternoon, everybody. It's my pleasure to be here to have some information sharing with all of you. I will have spent 4 hours. This time 2 hours, and next 2 hours. My topic for this class is GNSS reflectometry. Firstly, the principles and methods. So for this afternoon. So I will brief this topic at the beginning about remote sensing, because GNSS-R, its main application area is remote sensing. So let's see what is the main remote sensing techniques at this moment. So remote sensing is the acquisition of information about an object or phenomenon without making physical contact with the object, and thus in contrast to on-site observation. Remote sensing is used in numerous fields, including geography, land surveying, and most earth science disciplines. For example, hydrology, ecology, oceanography, glaciology, geology, and so on. So this graph shows the band information for the remote sensing techniques. It includes ultraviolet, visible light, infrared, and the microwave. So our topic is included in the microwave. So this graph shows the microwave techniques, including radiometry and radars. So in this band, the space is clear, so the signals could work well. So this picture shows the remote sensing could be implemented by optical and microwave. So the microwave will work all day and all weather because of the microwave performance. So based on the transmitter or not, So we can classify the remote sensing into passive and active. The visible, infrared, and microwave, all of these techniques could be worked in passive mode. However, the microwave could work in active mode. That means we can develop some instruments to transmit microwave in space and to collect the returns from the Earth's surface to get the physical parameters of the reflected surface. So this is the basic idea of the microwave active remote sensing. So the altimeters is one of the most important instrument for remote sensing. It has provided a wide range of application. For example, the wind vector, including the wind speed and the wind direction. And sometimes altimeters could give the surface ocean currents and its directions. So these two pics shows the basic idea of altimeters. So we will say the transmitter equipped on the carrier will transmit radio signals and collect its returns to itself. So the other techniques of active remote sensing is spectrometer. It operates by transmitting a pulse of microwave energy towards the Earth's surface, like this. The left, the bottom. So the difference between spectrometer and altimeter is the direction of the transmitter. So for the altimeter, the transmitter will propagate the microwave along its beneath. But for this one, the propagation path has a slant, has an angle with the Earth's surface. So the synthetic aperture radar is another active remote sensing techniques. The equipment is similar, but it will use the motion of radar antenna over a targeted region to provide finer spatial resolution than that from conventional beam scanning radars. So synthetic aperture radar has a more broadened application area than the conventional spectrometer. So this is the passive remote sensing, which is called radiometry. It is a set of techniques for measuring electromagnetic, including visible light. So it makes full use of the radiation from the Earth's surface. So it is simple than the spectrometer, altimeter, and the SAR radars. So because of it has no transmitters. So for example, this one is visible optics. It could be used for the inner wave, watercolor, and red tide. So the infrared radiometer could be used for the sea surface temperature. So for the microwave radiometer could get the salinity and the sea wind. So this is the basic idea of the remote sensing. So for the GNSS-R used for remote sensing, some idea is similar. some are not. For example, the overall boss will be not same, will not be the same. So for the geometry or some bistatic radar equations also have some differences. So I will move to the second point, GNSS-R introduction. So firstly, we will ask a few basic questions. How many GNSS constellations existed around the world? And what are their basic applications? And then what is GNSS-R? So we all know current GNSS constellations includes GPS from United States and Galileo from European Union, GLONASS from Russia, and the BDS from China. So this is the BeiDou from China's website. So you can get much more information from this website. So currently, BeiDou system enters into its third generation. So it is comprised of 30 satellites containing 24 in MEO. 3 satellites is IGSO and 3 satellites for GEO. So this satellite launched in March of this year is the 29th constellation satellite and also the second GEO satellite of BeiDou 3. Of course, GEO satellites is a typical one in BeiDou system. It plays a key role in featured services such as GNSS-R because of its specific geometry. Of course, it has other functions like short message communication and precise single point positioning and satellite augmentation systems. So the last GEO satellite will be launched in this month, maybe. So after that, BeiDou 3 will be comprehensively completed. So this is the visible satellites from today's website. So we can say there are around 14 satellites in half of the whole world and around 8 satellites on the western part of the whole world. So this is the ground tracks of BeiDou satellites from today's website again. So from this picture, we can say the BeiDou satellites could cover most of the latitude area from minus 60 degrees to plus 60 degrees in latitude. For the applications, we say all of the GPS applications BeiDou system could provide, but some applications GPS system cannot provide. Our BeiDou system can provide because of its short message services. For example, the fishery applications and some forestry applications based on the short message services, while the land mobile communication systems is not there. So it's quite useful. So for the positioning, navigation, and timing services, the multipass effect is harmful for the positioning. Sorry, it's harmful for the positioning accuracy. So usually for the GNSS receiver, will cancel this multipass effect. For example, we designed a specific antenna, like a choke ring antenna, to mitigate the multipass effect. So here we want to use this multipass as a signal sources for the remote sensing. So that means one person's noise is another one's signal. So let's see how to take advantage of it. So this slide shows the GNSS satellites signals with L-band microwave. So its wave, sorry. Oh, sorry. Its wavelength is around 20 centimeters. So the direct wave from the satellite to the receiver might be affected by some atmosphere effect, like ionospheric or tropospheric. So the propagation line will not be straight line. So it will have some curve, some time delay. So for the multipass, it's a bad boy for positioning accuracy. But here it's good for the surface parameters computation. So this is the basic idea. So it has the constructions like biostatic radar and its applications for Earth surface information. So from the left pictures, we will say the electromagnetic wave from the GNSS satellites far away from the receiver will be parallel incident wave. So the reflected waves will be come from the surface, and the relations between the reflected signals and the incident signals will have the linear relationship. So and it has some specific angle to calculate the power about the incident signals and the reflected signals. So if the signals from only one GNSS satellite, so we called it works biostatic radar. So if we collect the reflected signals from more than one satellite, like this picture from one BeiDou satellite, two GPS satellites, then we called it multi-static radar working mode. So these pictures shows the configuration mode. So the electromagnetic field at the receiver side has contribution from several GNSS sources, called it multi-static. As explained in previous class, maybe other professors talked, the different GNSS transmitters can be identified and separated from the rest of transmitters being received simultaneously by the modulation applied to each GNSS. That is PIN code. So these contributions correspond to signals that have propagated directly from the source to the receiver, crossing the atmosphere, as well as signals that have propagated down to the Earth's surface, scattered off its surface, and up to the receiver coordinates. So we will call rays or radio links these different branches of signals indistinctly. For example, this right bottom picture shows the black ball for ground, airborne, and spaceborne. The black ball is for active microwave remote sensing techniques. So for the dashed line with red colors, it is the GNSS-R. For the spaceborne, airborne, and ground-based separately. Of course, if the receiver is at airborne or a higher altitudes, for example, LEO satellites, the time delay and sometimes Doppler information can also be used to separate both radio links. For some applications, it's desirable that both direct and reflected signals interfere with each other, being then gathered by a single antenna pointing towards the horizon, the Earth's limb, or at a certain slant orientation. So in the following applications class, I will explain in detail about this kind of specific application scenario. So for the signal characteristics, we could use code delay or carrier phase information to do the physical parameters calculation. And sometimes we use the correlation function waveform, like the C code autocorrelation function. And sometimes we use the signal power to do this kind of calculation. For the application side, the physical parameters, we could get the sea surface height or some other sea state parameters like wind speed, wind direction, that is wind vector, and a surface a significant wave height. For the land applications, we could calculate the soil moisture from the GNSS-R primary observables or some secondary observables. Of course, these techniques of GNSS-R have some advantages. For example, it has many signal sources which are free, and we do not need to develop transmitter. We just use the transmitter from the navigation satellites, and the high temporal spatial resolution performance as the multiple navigation satellites and the L-band frequency signals can work for all weather and all day environment. Of course, the cost will be lower than the active remote sensing instruments. So the reflected signals from more than one satellite transmitter could be integrated for one receiver. So for this graph, the 3 satellites will have 3 reflected zones. So for the receiver, we can integrate these 3 zones into one parameters for the bigger area. And on the other hand, we can use the 3 different zones for different parameters. For example, these 3 zones will provide us 3 different similar parameters, like 3 wind speed. Or for these 3 different zones, we can provide 3 different physical parameters. Like this one will provide parameters on wind speed, but the middle one could provide us the other parameters, like surface height. So all of these applications could be implemented in the receiver equipped in this carrier. Of course, for these applications, some atmosphere effect will be integrated into the reflected signals as the microwave propagate path. But for this GNSS applications here, these contributions will be neglected. So this is a basic idea on GNSS-R. So thirdly, I will explain more on GNSS-R spatial characteristic. Firstly, it is a multi-static system. Its geometry and coverage. So this figure is compounded by the mosaic of glistening zones produced by the reflected GNSS signals. In spite of the distance between glistening zones, the coverage potentially achievable from a space-based GNSS-R receiver gives a synoptic view of many hundreds of kilometers across the track. That means this track, 1, 2, 3, 4, 6, 5, 6. So this 6 tracks, the across distance is about kilometers level if the system equipped on the satellite-based vehicles. So the time-evolving pattern of the observed areas reminds us an irregular comb. So that means the GNSS-R technique seeks to take the most of the large amount of GNSS signals reaching any spot on Earth simultaneously in a wide range of incidence angles. The amount of reflected radio links can be as large as the amount of direct radio links. So that means that how many navigation satellites are there, then how many reflected zones will be there. So of course, the Japanese regional QZSS and the India regional navigation satellite systems could also be used because of the satellite signals are similar as the GNSS satellite signals. So totally there will have around 150 transmitters in the space. So as a consequence of this large amount of simultaneously received signals, the spatial coverage obtained with a nadir-looking GNSS-R antenna corresponds to a gapped and irregularly sampled wide swath image of the surface beneath. Of course, the coverage area number are dependent on the receiver hardware and processing capability. That means if you want to get more than one track, you must make the antennas, down-looking antennas, cover this more broad area. So generally speaking, for the microsatellites applications, the down-looking antenna will cover 4 or less than 4 tracks. So in order to analyze the potential time-space coverage of a hypothetic GNSS-R aboard a low Earth orbiter, it is useful to focus on the specular points of the reflections, rather than the entire reflection glistening zones. So the specular point will here be understood as the point where the reflection would occur if the surface were perfectly smooth, with no any diffuse scattering component. As the LEO receiver and the GNSS constellations move along their orbits, the ground track locations of the specular points give an idea of the spatial coverage. For example, on the top of the graph, the location of GNSS reflections, specular points, assuming a GNSS-R receiver aboard LEO satellites at 800 kilometers altitude and 72 orbit inclination. And the coverage is for 1 day. So for the bottom graph, the coverage is for 3 days. So as shown in these two figures, the time required to irregularly cover the entire globe at mesoscale resolution can be as short as 1 day. If all visible GNSS signals could be used, the time scale could be shortened to be a few hours. Of course, if we launched more than one microsatellites to make a constellation, so the revisit time will be shortened more. So the same example is used to illustrate the number of simultaneously reflected GNSS satellites as a function of the latitude coordinate of their specular point on the Earth's surface, and accumulated in 1 day of observations. For example, this is based on GPS plus GLONASS constellation. So the time interval between subsequent along track points is 10 seconds. The black color value is for all visible GNSS transmitters, and its elevation cutoff is 0. So the red, green, blue colors for elevation cutoff around 30 degree, 45, and 60 degree respectively. So from the graph, we can say if the cut-off angle is bigger, then the number of simultaneously GNSS-R specular point will be less. So this graph shows our simulations. So we put the parameters incidence is around 98.7 degree, and the satellite height is 1,300 kilometers, and the antenna beam is 40 degrees. Then its averaged coverage is around 1.6, and the percentage is around 40%. Its average time revisit is about 8 hours. So to improve spatial characteristic of GNSS-R, the satellite constellation is used, such as the Walker constellation, determined by satellite number and orbit number. The table shows the results with the satellite number of 4. So for example, if we have 4 satellites, we could get 6 hours time revisit. So if we use the satellite number 8 and orbit number 1, which is similar as the CY GNSS from United States, its revisit time is about 4 hours. So that means it will observe the 88.9% of the whole globe in 4.5 hours. So the CY GNSS, its name is a Cyclone Global Navigation Satellite System from United States. It uses a constellation of 8 microsatellites to act as observatories, each carrying a delayed Doppler mapping instrument. These observatories will use 50 watts of power, less than a typical light bulb, and its weight less than 20 kilograms. In orbit, they deploy solar panels to reach the size of a foreground swan. A benefit of using constellation of microsatellites is that they will pass over the ocean more frequently than a single satellite would, resulting in a more detailed view of the ocean's surface, especially for the hurricane. So the satellites are capable of measuring 4 simultaneous reflections, resulting in 32 wind measurements per second across the globe. Each signals observatory includes the DDMI, consisting of multiple channel GPS receiver, low gain zenith antennas, and high gain nadir antenna. So the zenith antennas is for the direct signals, and the high gain nadir antenna is for the reflected signals. So the DDMI receiver will use a GPS receiver and antennas to provide unprecedented high temporal resolution wind field imagery of a tropical cyclone genesis, intensification, and decay. So this receiver contains a DMR, delay mapping receiver, and the electronics unit is on GPS. it has two Nadir pointing antennas for collecting GNSS signals. So one is left hand, the other one is right hand. So the zenith pointing antenna is to provide the geolocation and the satellite signals acquisition. So the signals, 8 satellites was launched by the air. So its air-launched vehicle was carried aloft by Orbital's modified L-1011 aircraft. Its name Stargazer, which took off from the Skidder Strip runway at Cape Canaveral Air Force Station in Florida. So it was launched in 2016 in December. And after around 1 year later, it provides the data for the public for scientific validation. So all of this information you can get more in detail from this website. It's from University of Michigan. Of course, you can get signals information directly from the website of NASA. So this is the graph from NASA's signals website. So from this graph, we can say it has much more wind speed values for the whole globe. But its coverage is only for the low latitude. You know, from this graph, we can say the latitude it covers around minus maybe 40 degree, and the plus 40 degree. So it's approximately 6 hours. And this data is from 2017 February. So the blue values indicate relatively low wind speed, and the yellow, orange, and red values indicate increasingly higher wind speed. So we can see this area and this area there has a cyclone. You know, it's a tropical cyclone, most of the east coast of the North America. So this is the spatial characteristics for the GNSS-R. Of course, we have done much more simulations for different Walker satellite constellations. But here, I didn't put more results. The fourth point is on GNSS-R signal. So, firstly, the GNSS signal is electromagnetic wave. So it scatters with complex process involving surface dielectric properties and topographic features as a whole system. So generally speaking, two limit conditions are typically distinguished and contrasted: specular or mirror-like reflection, like the top graph. The second one is diffuse scattering, like the bottom one. In most of the cases, the scattering process contains both types of contribution. That is, scenarios don't present either specular or diffuse scattering, but both of them in different proportions. So this is the fundamentals for the physical parameters calculation for the reflected surface. So for the specular or mirror-like reflection, the specular reflection process in which waves from a single direction and reflected into a single reflected one, like this one. So sometimes we call this rays or radio links, and it is the geometrical optics. However, for the diffuse scattering, the incoming waves are reflected in a broad range of directions because of the roughness. So this zone was called glistening zone. So let's imagine this receiver's antenna cannot cover this area. If the receiver antenna cannot cover this area, then the power will lose. So the antenna beam or the antenna angle is quite important, especially for the satellite-based applications. So even though the dielectrical properties will affect the reflected signals, the specular to diffuse regime is determined by the roughness structures of the surface topography rather than its dielectric properties itself. So specular reflection events are typically visualized in geometrical optics, in which the electromagnetic propagation is seen as a ray or radio link, a single ray bouncing off a smooth surface with a given incidence angle. Like this one, the incidence angle is theta. Reflects as another single ray or another single radio link in the same plane defined by the incident ray and the vector normal to the surface at the incidence point, like this one. This normal vector. But the azimuth is opposite. So for example, the transmitter is the right side, the receiver will be in the left side. So using this simple model, the specular point is the zero-dimension point, where the two incident and reflected one-dimension rays intersect the surface. So the imaging generated in such reflection events is called specular image, and it appears with the same size as the source and at the same distance below the surface as the source is in the front. So sometimes we called this phenomenon as forward signals instead of backward signals, because of the transmitter and receiver are located in the different side of the specular point. So the scattering with dominant specular component occurs in smooth surfaces, where the surface topography roughness has not significant features or spatial scales similar to the electromagnetic wavelength. That is, the roughness spectrum has contribution as much higher or a much lower wave numbers than the electromagnetic wave. So we change into another point of view to look this phenomenon. So it is wave optics. For example, for the specular reflection, the following Huygens-Fresnel principles. Every point on the wave front, and in particular on the sea surface, acts as a point source of the secondary spherical wave. That means the surface will act as the second signal source to transmit the signals to the receiver. So the scattered or reflected signal at any subsequent point between the surface and the observer is the sum of all these secondary sphere waves. So that means this Fresnel zone is not only one zero-dimension point. So it's a series of zero-dimensional point. So if the incident signal is a planar wave of given incidence angle and azimuth, the reflected signal results in another planar wave, equal incidence and opposite azimuth. And most of the energy contribution comes from the point sources of spherical waves located at a limited area on the surface, which was called Fresnel zone. Of course, this zone surrounds the specular point, so we call it two-dimensional specular zone or Fresnel zone. So for the diffuse scattering geometry optics picture, the diffuse scattering can also be pictured as geometry optics phenomenon, or more accurately, and wave optics models. The former approach requires the concept of surface physics, surface patches of size and curvature of the order of or higher than a few electromagnetic wavelengths. Because of the roughness, different facets are oriented towards different directions. Incident rays reflect off the facets, each facet producing a mirror-like reflection, which forwards the reflected rays towards a direction determined by the facet's normal vector and the incident ray direction. So in biostatic geometry conditions, the receiver only collects those rays reflected off facets with the appropriate tilt. So an appropriate tilt will occur at the surface coordinates xy when the facet at xy has its normal vector pointing towards the bisector of the angle formed by the incident ray at xy and the vector connecting the surface point xy and the receiver. So this is the basic geometry relationships. So the glistening zone is then defined as the area from where well-orientated faces might exist above a probability threshold. The glistening zone corresponds to the deterioration of the specular image described above. So keep in mind the points on the surface away from the nominal specular require higher slopes of the facet to forward the signal towards the receiver. And the rougher the surface, the higher the probability of largely tilted faces, meaning higher probability of well-oriented faces at coordinates far away from the nominal specular points. Therefore, the rougher the surface, the largest the resulting glistening zone. So, similarly, if the receiver antenna cannot cover the glistening zone, then the power will have loss. So this is a wave optics picture of the diffuse scattering. So for this phenomenon, we define then a ray radiation pattern, or simply a scattering beam, as a curve that relates each direction with the power forwarded towards it by the rough surface. So like this picture, so we have the ray radiation pattern like this. Note that the field received after diffuse scattering can be seen as the coherent sum of many individual radio link contributions. So that means the sum at the receiver location has the coherence properties on these signals from the surface. So each introducing a phase offset, because in diffuse scattering, the roughness scales are comparable or higher than the electromagnetic wavelength. The phase offsets of each contribution will be considered. Of course, if the receivers moving like airborne or spaceborne, or the surface is dynamic, that is the say, the individual random-like phase will be generated, called as fading or speckle. So the speckle noise is a series for the sea or ocean remote sensing applications. So signal coherence requires strong specular component of both platforms and the surface in static conditions. For these properties, the Beidou GEO satellite is quite good because the GEO satellite is stationary. Then we put a receiver on the ground-based, which is also static. Then we can detect or monitor real-time the interested area. So the detection of GNSS signals is done at the receiver by cross-correlating them against replicas or models. Like this one is the CA code autocorrelation function. The results of this correlation will be called waveform hereafter. So this is called waveform. So these replicas include modulation to identify the transmitters, working as nearly orthogonal codes like PIN code for GPS. For the modern GPS signals, it's BOC, and BeiDous also use BOC modulation. Or the BPSK is a popular one and has old history in the pseudo-random noise code. So each code or part of a code is assigned to a different GNSS transmitter so that a sufficiently long cross-correlation process yields power above the noise level if both signal and the replica contain the same code modulation, or it yields just noise if they are not coincident, like this one. This is the PIN1, the autocorrelation function. This is the zoom in for the a few code chips. The shape of the matching cross-correlation response waveform is determined by the code itself. For example, the GPS-C code or P code will have different Ys for the autocorrelation function because of the chip rate is different. So its correlation forms a triangle centered at the reception delay, and the length tall chip is a modulation chip. So of course, for the new BOC and GPS L5 and even Galileo E5, E6, it will have more narrow waveforms. Of course, for the BOC, it will have secondary peaks because of the subcarrier modulation. For example, for this one, the BOC will have the side lobe for the time domain, and for the frequency domain, it will have the side lobe frequency components. So this is of BOC 1.1. This is BOC 1.51. It has four secondary peaks. For this one, it has 1, 2, 3, 4, 5, 6 secondary peaks. So this signals has difficulties to be acquired because of the side peaks will affect the acquisition process in the receiver. And the frequency side lobe will make the power loss with the narrow bandwidth filter also. So then a purely specular reflection of GNSS signals produce a waveform shaped like the autocorrelation of its modulation code, like this one. This is for the direct signal for this. So this is for the reflected signal, this one, the black one, this one. So the code delay from the direct signal to the reflected signals is for specular point, this one, for this one, specular point. So if the surface has roughness rather than mirror-like, then the waveform will have shape changing and the tail will have slope. Will have slope. So the peak of the function, will be lower than the ideal view, which is triangular function. And the width of the waveform is much higher than the ideal one. So all this contribution comes from the glistening zone rather than only specular point. So of course, this is only the time domain. We also have the Doppler domain. So, and diffuse scattering, the waveform has contributions from a broad area, the glistening zone. The radial links between the transmitter of specular surface points and the receiver are longer than the path traveled through the specular point, of course. For this one, the eclipse with the red line eclipse, all the points on the eclipse have the same time delay from the specular point. So the time delay is like this equation, tau minus tau spec. So these equations for the eclipse is about this one. So this is a eclipse. So it's just a simple geometry relationship. So this is the delay spreading demonstration. For example, this one is the received waveform from the mirror-like surface. So of course, the direct signals triangular may be here. No, sorry, maybe here. No, sorry. At the around at the front of the in earlier than this red triangular. So for this spreading comes from the reflections from the glistening zone. So it's obviously same. So any contribution from areas away from the specular add power at the trailing edge, of the waveform. That is, power accumulates at delays greater than specular. So the waveform thus distorts. So its shape has changed. Its power scatters. So it's lower. The peak of the waveform is lower than this one. And the peak gets rounder and shifts towards positive delays. So the distortion with respect to the code autocorrelation function gives information about the roughness of the surface and its geophysical source. For example, wind blowing on the sea surface. So this graph shows the Doppler domain. So delay and Doppler frequency properties at each point on the reflecting surface here given with respect to the specular point. The 0, 0 is the specular point. So for the iso Doppler line is the contour lines like this. These contour lines is for iso-Doppler frequency. So this eclipse is for iso delay points. So the scattering plane is the YZ, plane. The receiver in the positive side of the y-axis and the transmitter towards negative y. So it's opposite direction. So this is called forward scattering. So for example, this graph shows the 1 Ca cold chip intervals is around 1 microseconds delay or 300 meters range. So for the left one is the aircraft scenario. For the right one is the LEO scenario. The altitude is 500 kilometers. For the aircraft scenario, it's around 10 kilometers altitude. So this one is clear, but we have some ambiguity because of the intersects between Doppler and delay domain. But for this green line, for example, green line, there's no ambiguity because only same value for the intersects, of the Doppler and delay domain. So this is the simulation results. So we set the height 5 kilometers and the elevation angle is 60 degrees and the integration time is 5 microseconds. The Doppler resolution is 100 Hertz. So it's a spatial distribution of delay and Doppler like this one. And the spatial filtering of the delay like this is 3-dimensional. And the spatial filtering of Doppler like this one, like a sync function. And the joint spatial filtering has two peaks. So this is reflectivity and polarization. According to the Fresnel reflected relation shape, the scattered signals and the incident signals has this relationship. So the detailed formulation of the polarimetric behavior of the GNSS reflected signals is embedded in the scattering series of microwave. However, the details of these series are not required to understand some general polarization aspects of the reflectometry GNSS. So the GNSS signals are transmitted at the right-hand circular polarization. The dielectric properties of the reflecting surface, together with the geometry, determine which amount of IHCP signal is reflected as IHCP and which one is reflected as left-hand circular polarization in specular line contributions. So it follows this Fresnel reflectivity relationship. So we can get these equations from the typical scattering theories into this circular polarization reflectivities from the linear polarization to circular polarization reflectivities value. So for this graph shows the cross-polar and copolar signals. For this intersects cross point, the angle was called burst angle. For the seawater, the different salinity will have different reflectivity values. For the foil, different moisture volume will affect the reflectivity value. So this is the basic idea on the reflectivity. So from the curve in this graph, we will know the ratio between the cross polarization. For example, right to left, left to right. The ratio between the right and the left could also be used for the physical parameters calculation. So for the scattering theory, it will help understanding the limitations of a set of different most used approaches and approximations. And it will focus on the biostatic Rita equation for GNSS signals and the Kirchhoff geometric optics limit. And sometimes we use Kirchhoff physics optics limit. So this one is the geometric optics limit demonstration. So for the free space electronic magnetic wave propagation. So the electronic field and the magnetic field is the start point for this scattering series. So because the navigation satellites is far away from the receiver and the Earth's surface for the remote sensing applications. So we use the far zone approximation. The receiver is far away from the surface. So and the Kirchhoff approximation is also called tangent plane approximation. So it means that the surface fields need to be known, reason for which solving this equation for realistic scattering problems yields to ensure mountable numerical complexity, and approximate models are necessary. So this necessity has spurred the development of more than 30 approximate models, valid and different limits and conditions. So some this literature gives the review and classification description in detail for these 30 models. So in most of the GNSS-R scenarios, the receiver is far away from the surface. Then we used the far zone approximation. However, the far zone approximation still requires the computation of the tangential surface fields, tangential. The exact analytical expressions for such fields can be found in the form of integral equation, but they cannot in general be solved analytically, and further approximation have to be introduced. So it is for engineering, not for theoretical study. For example, we used the KGO models. The geometrical optics limit of the Kirchhoff approximation is one of the most used approximation. It was implemented in GNSS-R modeling and it assumes that the phase factor is stationary. That is, it has no derivative with respect to displacements along the integration area. That means the area is has no any additional phase offset during the integration time. Note that physically this corresponds to those areas in the surface from where the received phase is nearly constant. It also corresponds to those areas in where the surface is locally orientated such that its local normal corresponds to the bisector angle between the incidence direction and the directional pointing from the particular surface point. So, another approximation model is Kirchhoff physical optics. The numerical simulation implementation or realistic realization of the surface, such as Monte Carlo-like simulations, could be a valid method to evaluate the polarimetric response of GNSS signals. However, the numerical evaluation of the integrals might require that the surface sampling length must be shorter than the electronic metric wavelength. So these two literatures has given more detail about these two parameters. So summary, the Kirchhoff approximation can be applied when both the correlation length of the surface and its average radius of curvature are greater than the electromagnetic wavelength. For the radius of curvature to be larger enough, the surface vertical scale roughness, usually standard deviation of the surface height, must be small compared to lambda square. Note that this latter condition limits the surface vertical scale roughness with respect to its horizontal scale one, but it still permits large, provided that the L is long enough. So its geometric optics limit has validity when the standard deviation of the surface height is large compared to the electromagnetic wavelength. That is, the incident radiation has small wavelengths compared to the surface structure. It is also called a high frequency limit. So finally, the physical optics limit is also called a low frequency regime, and it requires both small vertical scale roughness and small slopes statistics. This table shows the validity of each limit of the Kirchhoff approximation. Of course, all this methodology assume the far-zone field. Of course, the approximation methodology might consider the frequency term of the electromagnetic wave, which is the factor resulting from the carrier frequency after taking into account the Doppler effects, which is the movement of the carrier, the receiver, or the reflected surface. Of course, we have some other popular models. For example, small perturbation method is a good model for small slopes statistics, whose standard deviation of the sea surface height and collision length below the electromagnetic wavelength. It is appropriate for Bragg scattering issues. The second one is a two-scale composite model. It sums the contribution of the large-scale roughness from KGO and the small-scale effect from SPM in the sea surface roughness, small scale, and the radius of curvature is smaller than the electromagnetic wavelength. So besides the non-coherent received power scattered from smooth and large slopes orientated in the appropriate direction from KGO, it is also possible to receive additional power from other non-specular mechanisms, such as diffraction and Bragg resonance. These mechanisms are produced in the sea surface roughness, small scale. So given that most of the Earth's reflecting surfaces present a continuous roughness spectra, the main problem of the two-scale composite model is to define the limit between large and small scales in which to apply KGO and SPM respectively. So the threshold is quite difficult to determine. So the third model is integral equation method. This is a unifying theory suggested in late 1980s to bridge the gap between KE and SPM, and thus it covers all roughness scales. The integral equations of the electromagnetic fields are solved iteratively from the charges and the electrical current on the sea surface. In the first iteration, only the induced current are used, which is Kirchhoff approximation. The second iteration in the small slope statistics leads to the SPM. So the AEM is computationally expensive, but quite accurate. This is why it's especially useful to serve as a reference to compare with the previous models. So the small slope approximation so this is some typical examples of the different models. So next we will say what the received GNSS signals like. Considering the GNSS structure, the received fields are the results of cross-correlating the scattered fields S and the well-known replicas R of the code modulation C for different delays tau and frequency f. So this is the equations for the BPSK code autocorrelation function. So, and this is a cross-correlation function with different tau I and different different tau and different FC. But this is tau I is integration time. So for the diffuse scattering, this electrical field, the P and Q is the polarization value. For example, P could be right hand, Q could be left hand. of course, this is integral formulation necessary, and it's appropriate to any conditions because it's a general equations is comprehensive. So but the computation burden is quite heavy. So some simplification methods could be used to make the computation burden lower. So for the biostatic radar equation for GNSS-R, it has phase random-like behavior limits the coherent integration time. So generally speaking, for the biostatic radar equation, it has a short coherent integration time and a long non-coherent average time. So of course, these two parameters sometimes have conflict because of the movement of or the dynamics of the transmitter, which is navigation satellite, and the receiver, for example, the LEO satellites, and the sea surface, which is the reflected surface, so movement. So the power waveform are typically modeled using the radar equation, like this one is from ZV in 2000 year. So this one is the biostatic scattering coefficient. So this parameter is quite important for the remote sensing applications. So like this one, it's an explanation for this sigma. So the biostatic scattering coefficient sigma is a function of mean square slope like this Q, and the P probability density function. So there is a different, there have different model to calculate this coefficient, like alpha Halley and CM model. So this is some basic equations. I will not explain in detail here. So we can see some numerical simulation for these equations. So the high dynamic of GNSS satellite and receiver platform would result in the distortion of delay and Doppler maps, that is DDM errors. So these DDM errors could reduce the accuracies of measuring surface parameters, like sea surface height or significant view height. So how to reduce or remove these errors is a key technology of spaceborne GNSS-R applications. So this is the GNSS-R signals. So the fifth topic tonight is the GNSS-R signals collection, receiving, and processing. We have two methodology. The first one is code replica. The second one is PIT. The code replica is similar as the GNSS receiver, the typical GNSS receiver. So we have some local code, and we get the signal from the sky, and then we have some correlation. So for the PIT, yes, this is a code replica. So this is the PIT. So for the PIT, we have one waveform, and the full power will include the code and sometimes the carrier. So for this methodology, the code replica will will be generated in the local receiver. Then which code you will use, you will generate, then the code you will get, the code information you will get. So some code you did not generate in the local receiver, then you will have you will not get their information. Oh, sorry.
Thank you, Dr. Yang.
Oh, sorry. Sorry. So this the PIT real waveform result is, this is some typical cases for the two different methodology. So this is a GNSS receiver we developed by ourselves. There are 5 main blocks: the antennas, the IF, and the sampling and the quantization, signal processing backend, and some working stations. So this is detailed information. So we must consider the noise issues like the thermal noise, sparkle noise, and the craft's trajectory issues, and the integration time, and some system errors. So we must consider. So this one is for the time synchronization problem. So for example, this one. So for the different time spoke epoch, we will align the waveform into one time epoch. So for the observables, we have 2 classifications. The one is primary observables, delay and delay Doppler waveforms. And we have some secondary or defined observables like delay the peak, specular delay, and the DDM area for the surface, DDM volume for the whole curve. This is some detailed information. So this is a DMR, delay mapping receiver, developed by ourselves. So it used a commercial chipset from Xilinx, and it is only 0.5 chip GPSC code. So this is a delayed Doppler waveform, 2-dimensional tau I. This tau I is not integration time. It's the TI is the integration time. The tau is the time delay. So this is our receiver. So this is the basic blocks. So this integrated spectrum and delay, and some phase delay, volume, and some spectral observables, and some polarimetric ratio. So I explained in previous slides. This is a software receiver designed by ourselves, and this is the interface. So we, from this one, you can see we test in the flight with 5,200 meters altitude. So this is some typical products type. So the advanced GNSS-R receiver. So in the future, or in this current time, many research scientists work on this area, like NASA, ESA, Spain, French, Germany, and ourselves. So some research direction like a multi-antenna GNSS-R receiver was planned to develop for multiple GNSS. So maybe one antenna for GPS, one for Beidou, one for Galileo, and so on. Secondly, it's multiple function GNSS receiver. That means the GNSS-R receiver can output more than one physical parameters, like wind speed, surface height, or even sea ice. Thirdly, is the multiple frequency GNSS receiver for both reflectometry and radio occultation applications, because the radio occultation uses the refraction signals. And single frequency signals has some errors from the atmosphere. So multi-frequency signals could be used to mitigate the atmosphere errors. Of course, the software receiver could be used for the scientific validation and for the data reprocessing or post-processing. So summary for tonight's presentation. GNSS signal could provide new opportunity sources of remote sensing, and the reflected signals are jointly determined by electromagnetic scattering characteristic, GNSS-R geometry, and statistical characteristics of the surface. Receiving and processing of direct and reflected signal, GNSS signals, is known. However, how to improve the signal-noise ratio of reflected signals, especially for spacebound scenario, still is a challenge. GNSS-R has advantage of low cost, low power consumption, and high spatial temporal resolution compared to existing remote sensing methods, so that it's suitable to be used in commercial remote sensing. So its applications will be focused on the ocean sensing, hydrologic sensing, and cryosphere mapping. So in the next class, I will introduce in detail about these three typical applications and some case studies. So thank you very much. I don't know whether the effect of my voice is good for all of you.
Thank you, Dr. Yang. We are appreciated too much your lecture. It's a very valuable lecture for our audience. We will see if anybody wants to ask questions. Yeah, Dr. Tian?
Yes, I'm here.
Yeah, Dr. Tian, don't want to ask. I see that nobody raised his hand, or is there any question?
So I think if anybody has no questions, I put my email address here. If you have any questions, you can send me email because my research group works on this area for many years. Since 2003, I work on in this area, and I have collaborated with European research scientists. And the Chinese government support us to work together with European partners. So it's quite good to work on this direction. So I hope all of you could have some time or energy to work on this and contribute your energy in this area and promote its applications in your country. Okay.
Okay.
Okay, so
Dr. Yang, again, thank you. We would like to remember all our audience that next lecture will be in Thursday in the same time.
Tuesday.
Tuesday, yeah, on Tuesday, the 9th
Yes.
of June, yeah, 9th of June,
Okay.
at the same time.
Okay.
Thank you again, and we hope to see you on Tuesday.
Okay, you are welcome.
Thank you, Dr. Jan.
Okay, thank you. Bye-bye.
Bye-bye.